So I'm going to try page 7 again. I had a little interruption, and it just, I guess I didn't pause the video correctly. So I'm going to be a little bit quicker than I might normally be on this page because I'm just going to talk through what I had previously done on a video that fouled up, and I just kind of didn't really want to start all the way over. So going to the document, what you want to remember is that we have 3 master equations that kind of help us go back and forth between rectangular systems and polar systems. Sorry, I got distracted for a little bit. Anyway, so they were x equals r cosine and y equals r sine theta. And of course, Pythagorean theorem helps us do that. So keeping that in mind, when we have something like 5x minus 3y equals 10, we can easily just grab this x piece, throw it in there, and replace x with r cosine and y with r sine theta. Very easy to do a substitution there. You'll notice that I have an r in common on both of these, and then I go ahead and divide by this chunk right here. That's going to allow that r to be by itself, so r would simply be 10 divided by that piece right there. So, you know, what I did do earlier in the video is I just put my calculator in polar mode. When I hit the y equals, it now says r equals. You'll see I kind of have something like that here, but if I hit r equals, notice when I hit y equals, it shows up as an r equals. You'll see the answer that I have for this question in there that we can double back on in a minute if we want to. But so for the second question, if you were to distribute x minus 1 squared, you get x squared minus 2x plus 1. When you distribute y plus 3 squared, you get y squared plus 6y plus 9 equals 10. And I noticed that on the last test, we had a very, very similar problem. And what a lot of people tried to do is they tried to do this little substitution that I did right here really early, and then they got very, very confused. If you have to multiply it out, you're better off leaving it in rectangular. That's a lot easier to multiply x and y's than all these r's and thetas. So that's what I did. So after I multiplied this out, I noticed the 1 and the 9 made 10, so that canceled, which is pretty nice. Second, you'll notice that I highlighted x squared plus y squared because that is r squared. And then I did exactly what I did on that one, where I replaced x with r cosine and this y with r sine. Now, what's nice about that when we get to this phase is on this particular line, you're going to notice that every single one of these terms has an r in common. So I factored an r out. And so if we factored an r out of r squared, we're left with r. Factored an r out of this, we're left with a 2 cosine. And factored an r out of the 6 sine, there we go. So again, the reason I crossed out r equals 0 is one of the possible answers, because the zero product property says somehow somebody has to be 0, so that if I multiply these values together, I get 0. But r equals 0 is a silly answer to the equation of a circle centered at 1, -3, and a radius of √10. I mean, that's just not what it is. So this is a silly answer, which we call extraneous. So the only way that this thing in here could be 0 is if r was +2 and -6 on the sine, because those would cancel these out and make 0 happen. And so that's what you'll see right here is I did graph this to validate my answer. I graphed it, and what you'll see on that window is it looks like an egg or kind of squashed out because the screen is rectangular, not square. But you can kind of tell that if you go over 1 and down 3, like this would be, that does look like a circle of sorts. Now, again, it's a little hard to see because of the size of the screen, but I could hit a zoom square, and that does look kind of like a circle. Now, it's a little blotchy because of the way the calculator calculates trig, but it's pretty close. Now, over here, again, y is r sine theta, so I just changed y to r sine, did a little division, and, of course, the reciprocal of a sine is a cosecant, no big. Like I said, got interrupted partway through, so started over. This one is very similar to the previous one, and I decided that number 34 and 36 kind of go together, so I just decided to kind of pop them together. 7 secants is 7 over the cosine. I did a quick cross multiplication here, and you notice that r cosine is one of our fancy little formulas for x that we listed above. See, r cosine theta is automatically x right there. So I just replaced r cosine with x, and there we go. We're done. Nice little vertical line. And this other problem, B, some people got a little confused about it on the test, but on our formula, the sign needed an r next to it. So I multiplied everything by r, because now that I do, I have r squared equals 10r sine, but r sine is y, so I could replace this portion right here, this r sine, with y. And we also have a nice little formula from above that says x squared plus y squared is r squared. So again, I could turn this right here into rectangular. And this is purely rectangular already. We just want to do a little bit more work on it. And so I brought the y across. And then to complete the square, I added 25 to both sides to generate the better version of the equation of a circle. So, okay, so that got me back to where I should have been. Now, let's go back up to here to 35. Now, I'm going to keep using the equations that I mentioned before. So this is r and theta. Here's r and theta. Here's r and theta. And all of these are polar forms, but it's a simple formula. We know that x is r cosine theta. We know that y is r sine theta. And this is super easy because we should know that the sine of any kind of pi over 6 is a half. And 10 times a half is going to be 5. We should similarly know that the sine of any kind of pi over 6 is root 3 over 2. Times that 10 is going to be 5 roots of 3. So that 5 roots of 3, 10 should make sense. It's one of those special right triangles that we have done a few times. Now, the tricky part is deciding a little bit about pluses and minuses. So a couple of ways to think about this, but negative 5 pi over 6 we should be aware of is down here in this quadrant where the sine and the cosine are both negative. So if this is negative times a negative, that should be a positive on the x. And similarly, if the sine is negative times negative is a positive. Now, in some ways that seems like, well, that's weird, but it makes sense because if my angle is negative, but it tells me to go backwards 10, it would pop me into the first quadrant. So it does make sense that it's positive. And then in a similar way, we should know that r cosine theta would give me the x value, and in the same way r sine theta would give me the y value. And you just want to remember that the cosine and the sine of any kind of pi over 6 is root 2 over 2. So if we were to multiply 12 by root 2 over 2, you get 6 roots of 2. That's pretty easy. So both of these guys are 6 roots of 2. And last but not least, negative 5 pi over 4 is actually in the second quadrant where the sine is positive, but the cosine is negative. That's a pretty small negative sign, but it is there. And then last, we're just going to be super duper lazy. I'm going to make sure my calculator is in all the right modes and go back to degrees because the problem is, and I'm just going to let my calculator do it. R cosine theta, that's the x value. Oops, I did not do that right. R cosine theta is the x value. And r times the sine of theta is the y value, and 230 degrees is in the third quadrant. So I think these are both going to be negative, and they are. Now, here's where I got to slow down a little bit. So I want to prove that some of these things have the appropriate symmetries. And so I have some tests for symmetry right here. And we should know already before we start this thing that if it's a sine, it's going to have some kind of a y-axis symmetry. So it's going to fit one of these things really, really well. So what I'm going to do is I'm going to try this one. So I'm going to replace r and theta with a negative r and negative theta. So r becomes negative r, theta becomes negative theta, times 2 is still negative theta. Now the awesome thing is that we know that the sine, the cosecant, and the tangent, and let me try and think if there's anything else in there. These are the odd functions. They're odd, which means if you replace x with negative x, those come out in front. And that actually makes life very easy for this problem, because we've talked about this many, many times. That means if we were to factor that negative out, then I could cancel these two minuses out right here. And I got back to the original problem, and that validates that it in fact does have that y-axis symmetry, that's actually a good thing, and that totally works. Now, the part that gets a little bit hard to follow is that if this one worked, there's no way that one can work. So I'm going to try to avoid this guy, and I'm going to go with a slightly harder version right here. Because one of the things that we learned, or maybe I should try this guy down here. I think I will try this one. I'm going to find out if this one has origin symmetry, because I'm not really sure if it does or not. So I'm going to replace r with r, according to this, and I'm going to go in and replace theta with theta plus pi. So this is 12 sine 2 theta plus 2 pi. Now, this is really a pretty nice one, because we're talking about the idea that we have the sine of alpha plus beta. So I'm going to go ahead and use my nice little sum and difference identity to see what I can do. And this looks like it's going to be terribly difficult, but it's really not that bad. So we start out with the sine of the first, cosine of the second. Oops, I put a theta there and I shouldn't have. I'll be right with you. 2 pi. And I'm going to go with a plus, a cosine of the first, and a sine of the second. Now, that looks like I did a whole lot of work, but there's something really, really nice that happens right here, because I happen to know that the sine of 2 pi off of the unit circle is 0. And I also happen to know that the cosine of 2 pi off of the unit circle is the number 1. Well, if you put that together, 12 times the sine times 1 is just 12 sines. And then 12 times the cosine times 0 is 0. And you'll notice that since all of this stuff canceled out, I got back to the original problem, which proves it has origin symmetry. And that actually brings me to something really important, which I don't have enough room to write right now because I'm writing big. But if it has y-axis and it has origin, it automatically has x-axis, because you either have one symmetry or you have all three. This thing's got all three. So last one for our video, it's a cosine, so I'm pretty sure we got x-axis, which is going to be good. We're going to use this identity right here. We're going to replace r with r. We're going to replace theta with negative theta. Now, I listed the odd functions here, but all the other ones were even. So what happens in even functions is the negative just disappears and goes away. And so clearly, as that negative just gets disappeared, it comes back to the original function. Now, that's pretty good. That shows that it does have x-axis, but the question is, does it have all three, or is one and done all we got? So what we're going to do is one other thing. We're going to check y-axis by replacing r with negative r, and we're going to replace theta with negative theta. Now, again, just like the last problem, we said that that negative just disappears, which is fine. But if we wanted to get this r by itself, if we multiply both sides by -1, we have something kind of different that happens, because if this is true, we knew that it was a limicon that was actually extended to the right on the x-axis, whereas this one is now extended to the left on the x-axis, and that's completely different. That's not right. That is, doesn't have that symmetry. So the x-axis is a yes. The y-axis is a no, which means automatically the origin is a no as well. So we cannot have any other symmetries other than x-axis alone. So when we graph this, we should not expect to see anything crazy. So let's just do that real quick, put that in function and polar mode, and boom, we got it. 8 plus 4 cosine theta. I should see a nice limicon extending to the right 12 units. I'm not going to see it perfectly because it only goes out to 10, but you can see it's going out here to about 12, but it's only going to the left about 4, because 8 take away 4 is 4. So it worked pretty good, and I will see you for the last video in a little bit for the page 8. Bye-bye. Have a good one. Bye-bye.